volumetric heat generation. So uniform volumetric heat generation of Q equals to 10 raised to the power 6 watt per meter cube. So here, in this situation, there is heat generation. So we need to consider it also. So, and then, and has a thermal conductivity. So the thermal conductivity of the rectangular hot object or channel is given as well. And we are also told that the inner and outer surface of the channel experiences convection. So we have convection with fluid temperatures of T infinity equals to 50 degrees Celsius, and T infinity at the outer part is 25 degrees Celsius. And the convection heat transfer for the inner and outer are respectively given. So in this situation, we have all the information that is required to solve this question has been given. Okay, so let us see how first approach to attend to this question. We have been told derive and solve the mathematical solution for the temperatures at node. We want to determine the temperature at node 4, which is this node, and then at node, so somebody's coming, and then similarly at node 7, this node 7, and at node 9, so this is node 9. So these are the nodes that we need to determine the temperatures using the final difference method for two-dimensional system. So here we are told delta y equals to delta x equals to, how much is that? 25 millimeters. So that gives us 0.025 meters. Okay, so if you look at this question, the heat generation is given per unit volume, which is 10 raised to the power 5 watt per meter cube. And we don't have any information about the thickness of this rectangular channel. So we assume, so basic assumption. So first assumption over here is that thickness, we assume thickness equals to 1 meters. That's the thickness of the rectangular channel. So if we want to determine the finite or derive the mathematical solution for the temperature at node 4, so let's say consider node 4. So node 4. So we are going to extract the node 4 onto this particular slide. So we have a situation like this. Okay. Now we know that the neighboring nodes of node 4, one of them is node 5, node 2, node 8, and node what? Node 3. So clearly, we'll have a situation like this. Okay. So this also goes that way. Okay, so we have node 3, node 2, node 5, and then similarly node 8. So as usual, we are going to divide this portion into equal half like this. Okay, be careful. This section consists of convection situation. So your division will never affect it because it's an empty space. This is air. So the whole of this region, in this region, it is air. So the division does not affect it. So it only stops at this section. Okay. So now clearly we know that this vertical distance equals to delta y, this horizontal distance equals to delta x. So now this becomes delta y divided by 2. This is delta x divided by 2. Okay. So now, yes, so I forgot to indicate our node. This is node 4. Now, we'll use the fundamental equation. So we are going to look at the heat transfer from node 5 towards node 4, heat transfer from node 8 towards node 4, from node 3 towards node 4, from node 2 towards node 4, and also by virtue of the convection situation. So here we have T infinity I, which is the inside part, and then the heat transfer coefficient I, in this way. Okay, so I'm going to start with 2 first, and then I'll move in anti-clockwise direction. Okay, so from Fourier's law of heat conduction, we know Q equals to K A delta T divided by delta X. Okay, so I'm assuming that I've pushed the negative sign inside. So this is the whole backbone of the way of this solution. So now if I want to find the heat transfer from node 2 towards node 4, it is going to give me K, which is the heat transfer coefficient, the thermal conductivity, times the area. How do we determine this area? The area, the surface area that is receiving the heat, it is this area, this length times thickness. Okay, so it is going to give me delta X divided by 2. So this thing is very highly sensitive. Okay, so we'll have delta X divided by 2 times 1. So 1 is the thickness times the temperature difference. So it's going to give me T2 minus T4 all divided by the heat is transported in the y direction. So that is the thickness through which the heat is transported. So that gives me delta y. You understand? Plus, then again we have, I'll consider the node 3. Okay? So I'm going to consider this node. So then I'll have, so again, the heat transfer, so I have thermal conductivity. Thermal conductivity is constant for all the situation. Because we are dealing with the same material, the same rectangular surface in this way. Okay, so that we'll have the heat is transferred from state 3 towards node 4. So the area is going to give us this length, which is delta y, divided by, times the thickness. So this thickness, be careful. So this thickness, so that gives us 1, times the temperature difference. So that gives me T3 minus T4, all divided by delta what? Delta X. Plus, now we have, again, node 8. So again, thermal conductivity times delta X times 1, all into bracket, T8 minus T4, all divided by delta what? Delta Y. Plus, again, we'll consider node 5. Okay, so let me shift this thing upwards a bit. Okay, so node 5 is going to give us if you look carefully at node 5, we have K times the area. So which area are we talking about? It is this thickness times the vertical distance. So that gives us delta y divided by 2 times 1. Sorry. So this thing is very sensitive. So as if you'll be writing like you are in kindergarten. So, okay, so now we have, yes, times 1. All right. Then times, we have, again, delta, T5 minus T4 all divided by delta X. Okay, plus, again, now be careful over here. We are considering the convection part. So convection part, we have convection on this surface and convection on this surface. So it is going to be 2. So we have with respect to this surface and with respect to this surface. So we'll have a situation like this, plus, again, what is the formula for convection heat transfer? Q equals to H times area times delta T. So these are the 2 primary equations we required in solving questions like this. Number 1 and then equation number 2. These are all the important equations that we required. So following the convection, so we have heat transfer coefficient is given by HI for the inside part times the area. So how do we determine the area? It is this distance, delta X divided by 2 times the thickness. So we have delta X divided by 2 times the thickness times the temperature difference. So we have T infinity I minus T4 plus, then we consider this section as well. So that part is going to give us delta Y divided by 2 times 1, okay, times, oh, so I forgot to bring my, the heat transfer coefficient. So the heat transfer coefficient should come. So we have HI delta Y divided by 2. Okay, so then times 1 into bracket T infinity I minus T what? T4. Okay, so plus heat generation. So heat generation we have plus Q dot. Okay, so now be careful over here. The heat generation times the volume. Okay, because all these quantities that we have written here, all these, they are all in watt. But the unit for Q dot, the unit, its unit is in watt per meter cube. So it means we need to multiply this by the volume. Okay, we need to multiply this by volume, and volume is meter cube, so that this will cancel out, and then this unit will conform with these other ones. You understand? So if you don't multiply by the volume, then I'm afraid you'll get a wrong answer. So how do we determine the volume of the geometry? It is this volume plus this volume. Okay? So this is called a 3/4 node. So it is misbehaving now. Let me change. Yes. So we have okay. So and you can find the volume of this first, then add to the volume of that. So we'll have delta X, okay, times delta Y divided by 2, okay, times the thickness. So times the thickness is 1, plus, again, this delta x divided by 2 times delta y divided by 2. So I'll have delta x divided by 2 times delta y divided by 2 times 1. That is it. Okay, so now if you equate the whole of this to 0. Okay, so we equate it to 0. So that at the end of the day, if you substitute all the parameters, you substitute the value for HI, the value for K, the value for all the temperatures, then except T4, which is unknown, then eventually we will have T4, okay, T4 will be equal to 94.44 degrees Celsius, okay? So, and I will not go into all this detailed mathematics, but the final answer for T4 is given by this equation. Okay, so now quickly let us move on to the next node, which is node 7. You see, so we want to determine the value at node, the temperature distribution again at node 7. Okay, so with respect to node 7, we'll have a situation like this. So consider, sorry. So for node 7, now let us draw the node 7 is given by the neighboring node of node 7 is node 8, and then node 3. Node 8 and node 3. See, it's here. Node 3 is this, then node 8. Then we have insulation on the left side. So, and then we have convection at the bottom of node 7. So we need to consider all this convection aspect. Okay, so we have a situation like this. See? So okay, so now okay, so now I have, this is node 8, and that is node 3. Okay, and then we have convection. Sorry, we have insulation. The whole of this is insulation. This side. Insulation. And then we have convection. So this is node 7. And then we have convection over here. This is convection. So this means this is air. You understand? So as usual, we need to divide this into 2 equal parts. The whole of this section is solid. This is solid. So the division only affects the solid part, like this. Okay? It cannot go into the air, so we cannot divide this. Neither can we divide because this is insulation material. You understand? There is no heat transfer with respect to the insulation material. Okay? So carefully, this becomes delta y divided by 2. This is delta x divided by 2. Okay. So now, maybe let's start with node 7. Node 3. Okay. To node 7. The heat transfer from node 3 towards node 7. So this is going to give us, again, this is a conduction situation. So I'll have a situation like this. So K, thermal conductivity, times the area. So how do we determine the area? It is this thickness times this length. So that gives me delta x divided by 2 times 1. Okay, so then into bracket T3 minus T7 all divided by delta what? Delta, we have delta y. So the whole of this distance is delta y. Plus, again, I'll consider node 8. So heat transfer from node 8 towards node 7. That gives me thermal conductivity, delta y divided by 2, okay, times 1. 1 is the thickness into bracket T8 minus T7, okay, all divided by delta x. Okay, then let us consider the convection part. The convection part at the bottom of node 7. So again, the convection part, this is going to give us this distance, which is delta x, times the thickness. Okay, so plus, now we know heat transfer coefficient, this is HO. So the heat transfer coefficient for the outer, so then times the area. So how do we determine the area? Delta x. See, delta x divided by 2 times 1 times into bracket T infinity O minus T7 plus, now the heat generation. So heat generation part is going to give me Q dash times the volume. So the volume now is given by this, the volume of this region. So means I'll have delta y divided by 2 times delta x divided by 2 times the thickness. So that gives me the volume. So I have delta x over 2 times delta y divided by 2. And this is what we call a quarter node. So times 1. So all of this should be equal to 0. Somebody will say, why we didn't consider, let's say, to the left of node 7. There is nothing at node 7. To the left of node 7. So it is insulation. So there is no heat transfer from any particular region of node to the left of node 7. Okay, so we ignore that section. You understand? So now, then we equate everything equals to 0. So eventually, we will find the temperature at, So we will determine the temperature at state 7. So again, if you substitute all the terms into the equation, you get T7 equals to 95.6 degrees Celsius. Okay, so that is it for this particular part of the question. Now we move on to the last node, which is node 9. Okay, so again, let us see how node 9 looks like. So where do we have this? This is node 9. Node 9 is this. This is node 9. And the neighboring node of node 9 is node 10. Node 8, there is convection at the bottom of node 9. And then at the top of node 9 is node 5. Okay, so now let us consider node 9. Okay, so we have over here node 9. So now we will sketch the neighboring nodes of node 9. So we'll have, let's say, horizontal like this. And then we have vertical line. So this is node 9. To the left of node 9 is node 8. To the right of node 9 is node 10. To the top of node 9 is node 5. And then we have convection. Sorry. We have convection at the bottom part of node 9. So we have convection here, convection. So this is convection situation. Now, as usual, we're going to divide the solid part, the solid region, into two, like this. Okay, so this same as this. Okay, now we'll take them one by one. Then we will solve. Now the heat transfer coefficient, so the temperature over here is T infinity O. So then we have, we have H infinity 0. So quickly, let's continue. Let's start with, I'll start clockwise, starting with node 8. So now I'll have node 8, I have thermal conductivity times delta Y divided by 2, which is the area, times 1, okay, times temperature difference, T8 minus T9, all divided by delta what? Delta X, plus, again, we will have node 5. So for node 5, we will have K delta X, okay? So the whole of this, delta X, times 1. So 1 is the thickness. Okay, so then we have into bracket T5 minus T9, all divided by delta Y. Okay, plus quickly, node 10. So we'll have thermal conductivity, then delta Y divided by 2 times 1. Okay, so times the temperature difference, T10 minus T9, all divided by delta X. So now we are left with the convection part. So the convection part is occupying the whole of this. So it is going to give me H times, so H infinity O times the area. So area is giving me delta X, full delta X, times 1 times the temperature difference. So T infinity O minus T9. Then plus heat generation. So heat generation part is going to give me Q dot. Then I'll have delta X, okay, times delta Y divided by 2 times 1. All should be equal to 0. So eventually, if you solve for T9, okay, so it will give you, T9 will give you, if you substitute all other terms into the equation, you get 79.76 degrees Celsius. You can cross-check if you go back or if you, after this particular section. Okay, so that is it for this particular question. And I would like to take and move on to the next question. So if there is any question, let us discuss. Otherwise, I'll move on to the next question. Okay, so let's see. So I'm coming. Let me see if I can upload the other question onto the platform. So now, let me see. That's it. So, can you see the question, please? Can you see the question?
Yes, Doctor.
Yes, Doctor.
Okay, thank you, thank you, thank you. So, let's start with this question. Now, in this question, we are told that consider a square channel shown in figure question Q1 operating under steady state condition. Okay, so now the outer surface temperature is given by Ts equals to 30 degrees Celsius. So outer surface temperature, this one, this temperature. Ts is given by 30 degrees Celsius, and it's maintained by a very thick aluminum plate. Okay, so this is the aluminum plate. And the heat transfer from the aluminum plate to the surrounding can be negligible. Okay, so heat transfer from the aluminum plate, okay, to the surrounding can be negligible. Okay, so means there is no convection from the aluminum plate to the surrounding. However, the coolant flows in the sink. The coolant flows in the sink, and the inner surface experiences convection heat transfer with temperatures and heat transfer coefficient giving us T infinity. So we have T infinity, okay, equals to 100 degrees Celsius, and then heat transfer coefficient is given. Now, the node network of the problem consists of 12 equally spaced nodes with x equals to delta x equals to, yes, so here we are told delta x equals to delta y, and this equals to 0.012 meters. Okay, so like this. Now, the thermal conductivity of the body is also given 30 watt per meters per degree. The temperature for the several nodes, okay, T1 is given, T2 is given, all this way up to T12. So they are all given. Write down the final difference equation required to calculate the temperature of the following nodes. So we have to consider first node 4. Where is node 4? This is node 4. Now, the neighboring nodes of node 4 is node 5, node 1, and node 7. And then we have convection to the left of node 4. So this is the situation we need to consider first. Okay, so now let's proceed. Very interesting question indeed. So now we will have, let me draw the diagram for node 4. So we have a situation like this. Okay, so then node 5 will be somewhere here. Oh, sorry. Yes, to the right is node 5. And then to the bottom is node 1. At the top is node 7. And then we have convection. Okay, convection situation. So there is air. So T infinity is given. H infinity. You can say H infinity is also given over here. So as usual, you see these sections are all solid, these sections. So just divide the solid part only in this way. Okay? Like this. So this distance is the whole of this from here up to this portion is delta y. And this is delta x divided by 2. If there is another node over here, in which the whole of this section is solid, then we can extend this. But the whole of this is air. There is no way you can project this into this airspace. You understand me? So now we will start with calculating, starting with note 7. So as usual, again, using the two fundamental equations, Q equals to Ka delta T divided by delta X. And then we have Q equals to HA delta T. So this is conduction, this is convection. Okay, in some situations also, you can have heat flux. Heat flux. So then later maybe we'll consider a situation where we have heat flux towards a particular surface. Okay, but now one thing you need to know in this question, let's see, there is no heat generation. So far, there is no heat generation. Yes. So heat generation term is absent. We only have thermal conductivity, heat transfer coefficient, all these things are given. Okay, so assumptions. So basic assumption to start this question is that one, no heat generation. And then number 2, what can you think of? So thickness, the thickness of the slab equals to 1 meter. That's the assumption. Otherwise, then again, without making this assumption, it's very, 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 very difficult to proceed with the question. Okay, so now we start with note 7, heat transfer from note 7 towards, towards note 4. So this is note 4. Then we will have K, as usual, thermal conductivity, times the area. So what is the area? We have the delta X divided by 2 times the thickness. So delta X divided by 2 times the thickness, okay, all times the temperature difference. So we have T7 minus T4, all divided by delta Y, plus, again, I move on to T5. So this gives me K delta Y, okay, times 1 times delta, times T5 minus T4 all over delta X, plus, again, this gives me how much is that? We'll consider node 1. So K, again, times delta X divided by 2 times 1, all right? So then times the temperature difference, T1 minus T4, all divided by delta X, delta Y. Then we consider the convection part. So convection part is the whole of this surface. Okay, so I'll have H times, H times the area, which is delta Y, times 1, times T infinity, minus T4. That is it. So heat generation, Q equals to 0. No heat generation. So Q, here Q equals to 0, like this. So then you equate the whole of this to 0. That's all. Then you substitute all the terms inside. Okay, so if you here, and I have not been able to solve for the temperature T4, but you see, in some questions, you need to express or simplify the equation into its simplest form. Then you have about 3-4 equations, then you solve them simultaneously. Or, and according to certain questions, you are only allowed to simplify the temperatures. So let's say in this form. So we will have 4. The final temperatures is going to be 4.04. Okay, T4 plus 2T5 plus T7 equals to minus 82. Okay, so you can leave your answer in this form. Nobody will arrest you. You understand? So if you don't know the values for T, T7, T5, you can leave it in this form and say maybe this is equation 1. Then you solve again for a different node, then you get equation 2. Then for a different node, then you get equation 3, then you solve them simultaneously. Alternatively, you can just leave your answer in this form. Okay, so now quickly let us move on to node 5. So in node 5, oh, sorry. So in node 5, we have a situation like this. So you see, the neighboring, what are the neighboring nodes of node 5? We have node 6. Sorry. We have node 6. The neighboring nodes of node 5 are node 6, node 2, node 8, and then node 4. So this thing is misbehaving now. I have to see how to remove it. Yes. Okay. So now, if we take out node 5 by drawing the whole structure, we have this. This is node 5. Neighboring node of node 5, we have node 6, we have node 8, we have node 4, and then node 2. So what do you think about these nodes? Node 5. Node 5 is an interior node. Node 5 is what? An interior node. And for all interior nodes, what happens to it? So again, let's say we divide this into this section. Like this. Okay, so for all interior nodes, it's just a matter of adding T2 plus T4 plus T8 plus T6 minus T minus 4T5. See, minus 4T5 should be equal to 0. In this situation, the heat generation equals to 0. Okay, there is no heat generation. So for all interior nodes, we're going to have T4 plus T8 plus T6 plus what? T2 minus 4 T5 equals to, if there is heat generation, then you add it to this term. Otherwise, then the whole thing is equals to 0 in this way. Okay? So if you put, let's say, all the terms inside, okay, so eventually the question, yes, one other thing you need to know is that we can also use the normal equations that we used to do. Okay, so you get the same result. What I mean is, you take, let's say, T4, okay, by considering the heat transfer from T4, you have K, okay, times delta Y, okay, so this area times the thickness. Thickness is 1. So times 1 times T4 minus T5. all divided by delta X. So plus K delta Y, delta X times 1, delta X times 1, you'll get the same result. So delta X times 1, this is the area. So we are considering this, okay, times T8 minus T5 over delta Y plus, quickly, so K delta Y times 1 into bracket T6 minus T5 all over delta X plus the final one, K into bracket delta X times 1, okay, into bracket times T2 minus T5 all over delta Y. All should be equal to 0. Now, if you substitute all the terms, okay, again, given that delta X equals to delta Y, so these terms will cancel in most of the equations. These terms will cancel, delta X equals to delta Y. Okay? Then eventually you divide through by K, then you eventually get the final answer to be this. Okay? So either you follow this approach or you follow this approach. It's the same thing. Okay? So now let us move off to note 7, which is a very important one. So note 7. So it's a very trickish one. So note 7. Now, in this note, what are the neighboring nodes of note 7? Note 8, note 4, okay? And then we have 10 over here. But again, later we are going to discover that this note 10 does not have any influence on heat transfer in this towards note 7. Because in our analysis, we only consider horizontal heat transfer and vertical heat transfer. We don't consider heat transfer from any angle. You understand me? So we only consider situations where heat is transferred from either in the horizontal direction or vertical direction. Any other direction, we do not consider the heat transfer from any other direction. Okay? So now we will have a situation like this. Okay. So this gives me note 10. And then I have note 8 and note 4. Okay, this is note 7. And then I have convection on this part. Okay, as usual, I'm going to divide this, the solid section, by this. Okay, so this is note 10. Okay, so that is note 10 over here. So again, this is delta X divided by 2. And this is delta Y in this way. So whichever way we start from, let's say if we start with node 8, I'll start with node 8. So there is conduction. I'm going to have K times delta Y. Okay, so times 1 into bracket T8 minus T7 all divided by delta X plus thermal conductivity. again, of the fluid, sorry, of the solid, K, then I'll have, I'm considering this one. It's going to be delta X divided by 2 times this thickness. So I'll have delta X divided by 2 times 1, which is the thickness, then times T4 minus T7 divided by delta Y. Okay, then plus the convection part. Plus the convection part. The convection part is given by the heat transfer over here. So we have the convection heat transfer is given, T infinity is also given. So I'll have, that is to the left of note 7. You see, there is convection over here. So again, I'll have H, which is the convection heat transfer coefficient, times the area. Now the area is going to be this. So this distance, sorry, yes, this delta Y divided by 2 times this thickness. Okay, so now I will have delta Y divided by 2 times 1. Okay, then times the temperature difference. So T infinity minus T7. Okay, so now we're going to equate the whole of this to be equal to 0. There is no heat generation. No heat generation. So this whole thing should be equal to 0 in this way. Okay, so now if you simplify this equation carefully, cleverly, then you will have minus 3 points, let me see over here, and 306, 302 T7 plus T4, okay, equals to minus 120. Okay, so that's the simplification of this equation. Now, the last one, again, we'll look at the heat transfer for note 10. Okay, note 10. Now, at note 10, the situation is like this. So the neighboring node of node 10 is node what? We have node 8, node 11, 12, and 7. So we have a situation like this. Okay, so like this. So this gives me 11, 8, and then this is 10, this is 7, and this is 12. So similarly, again, we're going to divide this into 2 sections, like this. This goes like this. The whole of this is solid. Okay? So now, this is delta X, and this is delta Y. Okay? So now, I'll have, if I want to start the heat transfer from node 11, so I'm going to start with 11. So this gives me conduction, K, thermal conductivity, times the area. So delta Y times the thickness. So delta Y times the thickness times into bracket T11 minus T10, all divided by delta X. Okay, so plus now the heat transfer at node 8. So this gives me thermal conductivity, delta X, okay, which is the area delta X times 1 into bracket T what? T8 minus T10. Okay, minus T10. Okay, so like I have told you, so there is no heat generation. Now, there is no way we will consider the heat transfer from node 7 towards node 10. You understand me? Neither do we consider the heat transfer from node 12 towards node 10. Because I've told you that we only consider heat transfer in the horizontal and vertical direction, in 2D only, not at any particular angle. So it means that we consider only the heat transfer in this direction and in the vertical direction. You understand? And also there is no heat generation. Okay, so there is no heat generation for this situation. And if assuming if there is heat generation, so if there is heat generation, then we need to multiply that heat, add the heat generation to this equation. So then that it could have given us Q dot times the volume. Now, yes, so very good. In this situation, how do we determine the volume? So the volume is such a way that you see the whole of this is half of a rectangle. So if I project this upwards and complete it, it's going to give me a rectangle. You understand me? So it is going to give me the area of this rectangle is going to be delta y, delta x times delta y. But if I divide it by 2, then that gives me the area of this section. So then it could have given me delta y, delta x times delta y, all divided by 2 times 1. Then that will give me the volume. You understand? Okay, so but here we don't have heat generation, so this goes away. So then eventually we equate this to 0. So similarly again, and the final equation reduces to this form. So we have T, let's see over here, minus, minus 30 T10 equals to minus 120. Okay, so if you solve this carefully, then again you will, let me see, 1,200. Okay, so you can solve this equation very easily. So T10, so 0 will cancel 0 over here. So then this goes into this. So this gives us 4. Okay, so 0 like this. So this would have, this is the final answer for this. Okay, so now I think this is the end of this particular question. Okay, so is there any question so far? So it is raining heavily over here. I hope you can hear me well. Okay, so please, if there is any question, let me know. Otherwise, I'll continue with the lecture notes. Okay, so I have targeted myself to attend to the lecture notes, okay, up to a certain portion. Okay, so let me upload the lecture notes immediately. Yes, so I think we have discussed this section of the lecture notes. We were Let me see. Yes, we have discussed this section also. I think we discussed this also. Yes, we were here as far as our last lecture was concerned. Now, let us recapitulate what we did. So we started by giving the definition for not-so normal, okay? So we were told that not-so normal is defined in this way, okay? It is given by N. It is the ratio of the convection heat transfer relative to conduction. Okay, so if we insert all these equations into the not-so normal, then again we will come across this particular equation. So not-so normal is the heat transfer coefficient, say convection heat transfer coefficient times the characteristic length divided by the thermal conductivity. Okay, so this is a very important equation. And what is the significance of not-so normal? You understand? So it's very, very important. How do you appreciate it in engineering? So that whenever you are given a very high not-so normal, so if not-so normal is very, very, very high, let's say in the area of 100, then it means that the convection situation is dominant compared with the conduction. You understand me? And then also, if we have a very, very low not-so normal of a fluid, then it means that the conduction situation is very dominant compared with the convection situation. So that's the basic significance of this not-so normal. And then we also define dynamic viscosity, kinematic viscosity, and so on. And important thing we need to also know is the velocity boundary layer and then the thermal boundary layer. So the development of the velocity boundary layer across a flat plate, okay, it is at a point where the velocity of the fluid is approximately equals to 99% of the free stream velocity, okay? And any point above the velocity boundary layer is what we call the inviscid flow situation. So now we also look at the thermal boundary layer. Okay, we also look at the thermal boundary layer, which is given by this. So the thermal boundary layer is the situation where we have T minus Ts equals to 99% of T minus Ts. Okay, so now we also define the Prandtl number. Prandtl number is the ratio of kinematic viscosity divided by the thermal diffusivity of the fluid. Okay, then we also look at Reynolds number, critical Reynolds number. Then we look at the three fundamental equations, governing equations for fluid flow across external surfaces. External flow, which is fluid flow across, let's say, solid surfaces.